Welcome to Implementing Programmable Interfaces for Huawei Networks. I am Mohammed Hamdi and I will be your instructor in this course. I have CCIE service provider and I have more than 18 years of experience in IP telecom and enterprise networks worldwide. This course presents the skills required from Huawei engineers to develop Python codes and build automated tasks for Huawei Datacom products. The course is presented in hands-on tabs to cover the following main objectives. Develop Python 3 codes with network libraries NetMiko and Napalm. Perform network automated tasks with Python 3. How to configure OSPF routing protocol in an automated Python script. How to run automated Ping IP connectivity test. This course is designed for Huawei Datacom pre-sales, post-sales, and network architects who want to automate their tasks with Python developed codes. Looking forward to see you enrolled in this course. Let's get started. In this video, I'm going to build a Python 3 code with NetMiko library to connect to Huawei router and run CLI command display IP interfaces brief. The output of display IP interfaces brief will be printed upon the execution of the code. NetMiko is a multi-vendor library to simplify Paramiko SSH connections to network devices. Paramiko is a library for making SSH version 2 connections, clients or servers. So we can define NetMiko as in this slide. NetMiko executes CLI commands to multi-vendor network devices over SSH connections established by Paramiko. Let's head to the lab now to implement the code that will be run on Linux desktop. In the lab we have a Linux desktop connected to Huawei NE40E router through a switch. We will write a Python code on the Linux desktop using NetMiko and Paramiko libraries to establish SSH connection to Huawei NE40E router and execute command display IP interface brief, then gets its output printed back to Linux desktop. Huawei NE40E router must be configured as SSH server to accept the SSH connections coming from Linux desktop, and in the code we will display IP interface brief on the router. So we expect this output to be printed in the Linux desktop. So now let's log in to the Linux desktop using SSH connection. Then we will go to Huawei directory created before and create new file. I'll name the new file as netmiko_Huawei. Then I will write the shebang to explain that this code is written in Python. Hashtag exclamation mark /user /bin /env space Python. Then I will import connect handler from NetMiko. Import connect handler. Connect handler will be used to initiate SSH connections to Huawei router. So now it's time to give the login details and the connection details for Huawei routers. I will name these connection details as NE40E router equal Then I will write the connection details in curly brackets. Then specify the connection details. First, the device type. The device type is Huawei, comma, the IP address that will be used to request an SSH connection. Let's check the IP address. Linux desktop must connect NE40E router through interface Ethernet 1/0/0. So let's check now. Ethernet 1/0/0, it has an IP address 10.1.1.2. So I write the IP address as 10.1.1.2, comma, the username of the SSH connection will be Huawei. It's configured before on the router as Huawei. And then the password. It's Hamdi H capital at 123. Then I'll close the curly brackets. Now I have specified the connection details required for NetMiko to establish SSH connection. Now I'm going to establish the connection using net connect equal connect handler then I'll give the connection details name, which is NE40E. Then I will output the execution of the command line interface command display IP interface brief. So I need to send first the command line interface command, which is display IP interface brief, using net_connect dot send underscore command display IP interface brief. And finally print the output. I have named net_connect parameter with connect handler using the connection details given, device type, IP address, username, password. Then I have sent CLI command using net_connect dot send_command display IP interface brief, and the output is named as output here. Then I print the output. Let's save the file now. ls-l to make sure that the file is created. Cat netmiko_Huawei will display the contents of the file. Now it's time to execute the code. I'll execute the code using Python and the name netmiko_Huawei. Now I have got the output of display IP interface brief of the router printed here using an automated script that connected to the router and get the output of display IP interface brief. Thank you for viewing this video. I hope it has a good value for you. NAPALM stands for Network Automation and Programmability Abstraction Layer with Multi-Vendor Support. NAPALM is a Python library that implements a set of functions to interact with different network device operating systems using a unified API. NAPALM automation community on GitHub for Huawei VRP, which is the OS of Huawei devices. We can find here all what we need about NAPALM, including how to install, using command pip install napalm-huawei-vrp, and a list of the supported APIs that can run and interact with Huawei devices. In this video, we are going to use getFacts API in a Python script to get general information about the router. Let's head to the lab to implement the Python script that will run on Linux desktop, which is connected in the lab to Huawei NE40E router. NAPALM requires SSH to be enabled on the router. So let's go now to Linux desktop terminal and go to Huawei directory, in which we create Python scripts for Huawei devices and create a new file named as napalm _get_facts, then enter. Here I'll create and write the Python script of NAPALM. I'll start by -ping #!user /bin/env space Python, and from NAPALM import get_network_driver. Then I'll create a new parameter named as driver to indicate that I'm going to interact with Huawei network device. So driver equal get_network_driver, then open a round bracket in which I'll indicate Huawei_VRP. Then I'm going to ask the Python script to open an SSH connection with the router. Before I ask the script to open the SSH connection with the router, I have to insert the connection details that will be used. The connection details are the IP address, username, and password. So I will create a new parameter named as device equal, then from the driver created above, I will indicate the connection details. The connection details are hostname, which is the IP address of the router. It's 10.1.1.2. You can make sure that this is the IP address that is configured. Huawei NE40E router has Ethernet interface 1/0/0 is connected to Linux desktop. So let's check the IP address configured on this interface using command display IP interface brief. This interface 100 is configured with 10.1.1.2. So the IP address here is correct. Then the username of the SSH connection is configured as Huawei. Then the password is configured as Hamdi H capital at 123. Then I will close the round brackets. Finally, I'll ask the script to open the SSH connection using device.open. After I open the SSH connection, I am going to use the getFacts API. So I will receive the getFacts API contents in a parameter named as getFacts, and this is device dot get underscore facts. This is the API of Napalm. Then I'll output the contents of getFacts using print get underscore facts. Let's save the file and make sure that the changes I have added is applied. List the files in this directory using ls-l, and then I'll use cat napalm underscore getFacts. This is a file that I have just created, and this is a script I have applied to the file. So right now I'm going to execute this script using Python napalm underscore get underscore facts. The Python code is now executed successfully, and this is the output of the Python code. Is a dictionary. The output of the Python code is getFacts parameter, which is printed here in this command print getFacts, and the getFacts parameter is the API of Napalm get underscore facts. We can see here the output in a dictionary. To clearly print the output of this dictionary, we can use pprint instead of print only. Let's check it, and back to the script again using nano napalm underscore get underscore facts, the name of the file, and import pprint, and instead of print getFacts, we will write pprint dot pprint getFacts. Save changes, then execute the Python code again. The result and the output of the Python code is now more obvious, and items of the dictionary can be read and viewed well. I can also modify the script to only print the host name item of the dictionary. So let's get back again to the script and print get underscore facts dictionary, the host name item in a square brackets, then save changes, then execute the Python code again. Now we have already printed the pprint of the whole dictionary, and we only printed the item of the host name of the dictionary, which is NE40E1. Thank you for viewing this video. I hope it can be a good value for you. In this video, I am going to build a Python 3 automated script with the support of Napalm library to interact with Huawei router and get info of IP interfaces of the router. Napalm stands for Network Automation and Programmability Abstraction Layer with multi-vendor support. It's a Python library that implements a set of functions to interact with different network device operating systems using a unified API. This is the list of the supported APIs for Napalm with Huawei router. In this video, we will run and test Get Interfaces IP API with Huawei router. Remember, to install Napalm for Huawei, we need to run pip install napalm-huawei-vrp. Let's head to the lab to implement the Python script that will be run on Linux desktop. Linux desktop in the lab is connected to Huawei NE40E router. Huawei NE40E router is configured as SSH server to accept SSH requests from Linux desktop. We will run the Napalm API to get general information of the router, like we are running on the CLI of the router, command display IP interface brief. On Linux desktop, I will create a new file named with the API of Napalm. I'll create the new file using nano napalm underscore get underscore interface int underscore IP. Enter. Now I will add the Python script here, starting by the shebang /user/bin /env space Python. Then I will import now get network driver of Napalm from Napalm, import get underscore network underscore driver. Then I will import bprint to be able to clearly print the contents of the get interfaces IP API. Then I'll create a new parameter named as driver. In this parameter, I will specify that I am working with Huawei VRP using get underscore network underscore driver Huawei underscore VRP in rounded brackets. And then I will create a new parameter named as device to specify the connection details that will be used to create SSH session for Napalm using driver, then open rounded brackets, then specify the host name which is the IP address of the router I'm going to connect. The IP address of the router that I'm going to connect is 10.1.1.2. So I'll specify here the IP address 10.1.1.2, and next is to specify the username of the SSH connection, which is configured as Huawei, and password, which is Hamdi H capital at 123. Then close the rounded brackets. And now I'm going to open the SSH connection using device.open. After we initiated the connection using device.open, I'm going to create a new parameter named as get interfaces underscore IP which will receive the contents of get interface IP API of Napalm using device dot get underscore interfaces underscore IP, and finally I'm going to print the contents of parameter get interfaces IP using pprint dot pprint get interfaces IP. Now I finished the script. I will save. Then to list the created scripts and file on this directory, we created Napalm underscore get underscore int underscore IP. We can review the script now using cat, then the name of the file. This is a script I have created above. And now I'm going to run the script using Python Napalm underscore get underscore int underscore IP. Now I have successfully received the contents of the API get interfaces IP, which specify each interface with information about the IPv4 configuration, like the IP address and subnet mask. Thank you for viewing this video. I hope it can be a good value for you. In this video, I am going to build a Python 3 automated script with the support of Napalm library to interact with Huawei router and ping a network device from the router. This is the list of the supported APIs of Napalm for Huawei devices. In this video, we are going to run ping API to ping remote IP from Huawei router. Remember, to install Napalm for Huawei, we need to run pip install napalm-huawei-vrp. Let's head to the lab to implement the Python script that will be run on Linux desktop. Linux desktop is connected to Huawei NE40E router. NE40E router is configured as SSH server to accept SSH requests from Linux desktop. We will run Napalm API on Linux desktop in a Python script to log to Huawei NE40E router and ping another device in the network. As an example, we will ping Linux desktop. On Linux desktop, I create a new file named as napalm underscore ping. And in the file, I added the Python script started with the shebang, and from Napalm import get underscore network underscore driver and import bprint. Then I created a new parameter named as driver to specify that I am working with Huawei VRP. It's Huawei device, and I created a new parameter named as device to specify the connection details that will be used for Napalm to initiate SSH connection with the router. And then I added device.open to open and ask the Python script to open SSH connection for Napalm. Now I'm going to use ping API. I'll create a new parameter named as ping underscore remote underscore IP equal device dot ping to call the API of Napalm, which is ping, and open a rounded bracket. In the rounded bracket, I'll specify the remote IP that I'm going to ping on. The remote IP is 10.1.1.9, which is the IP address of the Linux desktop. So after I ping, I'm going to receive the result of the ping, if it's successful or not, and if there is reply or request timed out. The result of ping will be received in this parameter, ping_remote_IP. So next is to pprint ping_remote_IP. So I can see the contents of ping_remote_IP, which is the result of ping API of Napalm. Let's save the script now and run the script using Python napalm_ping. I have successfully executed the Python script and I received success here, which is the output of ping_remote_IP parameter. And there is no packet loss, 0 packet loss, and props sent 5. We sent ping requests to Linux desktop, and this is the result. IP address 10.1.1.9, which is Linux desktop, replied to these 5 sent probes. Thank you for viewing this video. I hope it can be a good value for you. In this video, I am going to build a Python 3 automated script to configure OSPF for Huawei routers. OSPF will be configured on 2 routers with the support of Napalm library and 2 routers with the support of NetMiko library. In the lab, NE40E1 and NE40E2 will establish OSPF with each other on interfaces 1.0.1 using Napalm. NE40E-P1 and NE40E-P2 will establish OSPF with each other on interfaces 1.0.1 using NetMiko. Python scripts will be run on Ubuntu Linux desktop that can reach the routers using the management network. I'm going to log into Huawei NE40E router and check the OSPF configuration commands in CLI. I will log in to the router using command ssh Huawei at 10.1.1.1. Huawei is the username of the router and 10.1.1.1 is the management IP address of NE40E1. Now I have logged in successfully to the router. I will run command system view to go to the system view mode and execute OSPF configuration commands. I'll start by creating the OSPF process using command OSPF and 1. 1 is a process ID. Then I'm going to create the OSPF area, which is OSPF area 0. Then I'm going to specify the interfaces on which the OSPF will form OSPF neighbor relationships. I'll select interface Ethernet 1.0.1. I'm going to run command OSPF enable, and 1 is a process ID. Then area 0. If I run command display this in the interface view of 101, it will display the configuration in Ethernet interface 101. It didn't execute OSPF enable 1 area 0. Because I am working with VRP8, I need to run command commit to apply the changes. Then display this again. Now we can see that OSPF enable 1 area 0 is applied successfully. Same for the OSPF configuration of OSPF process 1. To make sure that it's applied, I'm going to run command display current configuration OSPF. We have OSPF 1 and area 0. We have to note now that interface 101 doesn't have any IP address configured here. I must configure the interface with an IP address so the OSPF can work on top of it. So I will add command IP address 192.168.1.1/30. Then run command commit to apply the changes. Display this. I can see now that the interface is configured with the IP address 192.168.1.1. This is all the configuration I need for the OSPF on the router. First, I had to create the OSPF process and its area. Then I had to go to the interface on which I have to enable the OSPF process using OSPF enable process ID and area ID. Finally, I have to make sure that the interface is configured with an IP address. So now I'm going to remove all this configuration and get back to Ubuntu Linux desktop and create the Python script using Nabal to enable OSPF configuration for router 1 and router 2. Undo IP address, undo OSPF 1 area 0, and undo OSPF 1. Sorry, I have to quit and undo OSPF 1 from the system view mode. It asks me that the OSPF process will be deleted. Continue. I'll choose yes. Then I'm going to run commit to make sure that the OSPF configuration has been removed. Display current configuration OSPF. It doesn't show the OSPF process 1. Display current configuration interface Ethernet 101. We cannot see the IP address and we cannot see the OSPF process 1 area 0. Let's quit from the system view mode and run command save to save the configuration. Then quit. I'm going to create a new file named as OSPF_config. Here I will add the configuration commands for the OSPF. OSPF 1 area 0 interface Ethernet 101, IP address 192.168.1.1, subnet mask /30, OSPF enable 1, area 0. This is all the configuration I need to enable OSPF for router 1. Control X, then save changes using yes. Now I will add the Python script in a new file. I will name the file as nabol configure OSPF. I start with the shebang hashtag !/user /bin /env space Python, then from nabol import get _ network _ driver, import pprint. Then I'll create a new parameter named as driver to specify to the router that I am working with Huawei VRP device using get _ network _ driver, then open a rounded brackets, then specify Huawei _VRP. Now I will create a new parameter named as device to specify the connection details for nabol to be able to initiate SSH session. Driver, and then open a rounded bracket, then the host name, which is the IP address of the management interface of router 1, then the username, which is Huawei, then the password, which is Hamdi at 1234, then close the rounded brackets. Now I will add command device.open to ask nabol to open SSH connection to the router. Before I load the configuration file of the OSPF, I will issue a command in a new parameter named as command. This command to display the configuration of interface Ethernet 101 using square brackets, display current configuration interface Ethernet 101, then close the square bracket. This command will be executed using nabol to make sure that Ethernet interface 101 doesn't have any OSPF configuration. I'll create a new parameter named as getInterface, and this parameter equals to device.cli and open rounded brackets, give the parameter command, then close the rounded brackets. GetInterface will call the API of nabol, CLI API, and execute command display current configuration interface Ethernet 101. Then I'm going to print get interface to see the result of executing this command. After I executed this command, I'm going to load the OSPF configuration file using device.load underscore merge underscore candidate. Then I'll give the OSPF configuration file I have added before, which is OSPF underscore config in rounded brackets. Then I will execute and apply the changes taken from the OSPF configuration file using commit underscore config, then rounded brackets. This is another API of Napalm to commit and apply the changes I have executed in OSPF configuration file using load merge candidate API. Finally, I'm going to execute again display current configuration interface Ethernet 101 and print the result of this display command, display current configuration interface Ethernet 101, to make sure that the OSPF configuration is applied successfully without the need to go to the CLI of the router and check for it. Now I'm going to save the Napalm configure OSPF file, execute the Python script in Napalm configure OSPF using command Python, then the name of the Python script file. The Python script now is applied successfully. First, I have got the result of display current configuration interface Ethernet 101, and it doesn't show any OSPF configuration here. And secondly, I had received this configuration and it includes the updated configuration I have added in OSPF configuration file, which are IP address and OSPF enable 1. Now it's time to get back again to the OSPF configuration file and update the IP address for router 2 nano OSPF underscore config. So I have to change the IP address of the interface from 1 to 2. Then save the configuration file and then get back again to Napalm configure OSPF file. Then here I have to change the host name to be 2 instead of 1. 2 is the management IP address of router 2. Then execute the Napalm script for router 2. Now the Python script has been applied successfully. Firstly, it doesn't show any IP address and OSPF commands enabled on the interface. And secondly, I have added the IP address and the OSPF command for the interface. Now I will log in again to router NE40E1 and make sure that the OSPF peer relationship is formed successfully with router 2 using SSH Huawei at 10.1.1.1. Then I will run command display OSPF peer. Now display command OSPF peer shows that there is an OSPF peer relationship established with 10.1.1.2 and the address of the peer is 192.168.1.2. I can make sure that the OSPF configuration is applied successfully to router 1 using command display current configuration OSPF. It shows that there is OSPF 1 and area 0. I can also run command display current configuration interface Ethernet 101. It shows that there is an IP address and the OSPF process 1 is enabled for area 0. Now I'm going to use Python script with netmiku to enable OSPF for router P1 and router P2 on interfaces Ethernet 101. So I'm going now to quit from NE40E PE1 and add a new file. I name this new file as netmiku_configure_OSPF. I will also start by the shebang /user/bin/env /python, and from netmiku I will import connect handler. Then I will create a new parameter named as NE40E equal the device type is Huawei to specify that I'm working with Huawei device. The IP address is 10.1.1.3. Username is Huawei and password is Hamdi at 1234. Then I'm going to close the brackets. So I have added here NE40E parameter and open a curly brackets. Then I have specified the connection details that will be used to initiate SSH connection using netmiku to router 10.1.1.3, which is the management IP address of NE40E P1. Now I'm going to ask netmiku to connect to the router using a new parameter named as net_connect, then connect handler NE40E. Now I'm going to do the same I have done before for the Napalm script using display current configuration interface Ethernet 100 to make sure that the interface doesn't have any configuration. I'll create a new parameter named as output net underscore connect dot send underscore command, then open rounded brackets. Then this is a command that I'm going to send using netmiku display current configuration interface Ethernet 101, then close the round brackets, then print output. Next is to create a new parameter named as commands, which is the configuration commands I am going to send using netmiku. I will define the commands in a square brackets. This is the first command I'm going to create, which is OSPF1, then area 0, then interface Ethernet 101, then IP address 192.168.2.1 and subnet mask /30, then OSPF enable 1 area 0, then close the round brackets, then use the output parameter to ask netmiku to send the configuration commands using send underscore config underscore set and the commands I have created above. Next is to print output. This will print all the configuration commands that have been applied to the router. Finally, I'm going to call this parameter again, output netconnect.send underscore command, and to display current configuration interface Ethernet 101 to make sure that the configuration above is applied successfully. Then print output. I'd like to add commit commands to apply the changes, because as I said before, I'm working with Huawei VRP8. Now I will save the script, then I'm going to execute the file python netmiku underscore configure underscore OSPF. Now the Python script with netmiku is applied successfully. It displays the interface Ethernet 101 before applying the OSPF configuration. It doesn't have any OSPF configuration here. Then it started to execute the OSPF configuration using system view, OSPF1, area 0, and then the interface 101, then the IP address configuration and the OSPF enable 1 area 0, then commit, and then it returned because it finished the configuration. Then it displayed the Ethernet interface 101 again, and it shows that the IP address is configured 192.168.2.1 and the subnet mask, and then the OSPF enable 1 area 0. Now I'm going to execute the same Python script but with router P2. So I will go again to the netmiku configure OSPF file. Then I have to change the IP address to be 4 instead of 3. 4 is the management IP address of router P2. And here I have to change the IP address that will be configured on interface Ethernet 101 to be 2.2 instead of 2.1, because 2.1 was assigned for router P1. Then I will save the script, and now I'm going to execute the netmiku configure OSPF file again. Now the Python script has been applied successfully with netmiku. It displays the interface Ethernet 101 without any IP address configuration or OSPF. Then it started to execute system view OSPF1 area 0 and interface 101, then the IP address and OSPF enable 1 area 0, then commit changes, then return and display again the interface Ethernet 101 with the IP address configuration added. I will log into router P1 to make sure that the OSPF peer relationship between P1 and P2 has been formed successfully. SSH Huawei at 10.1.1.3. Then display OSPF peer. Now there is peer format and the router ID is 10.1.1.4 on address 192.168.2.2. So in the lab, from Ubuntu Linux, I could get to NE40E1, NE40E2 using the management interface and applied Python script with Napalm to apply OSPF configuration for them on interface Ethernet 101 to form OSPF NIPO relationship between router 1 and router 2. And I did the same for router P1 and router P2, but with Python netmiku script. Thank you for viewing this video. I hope it can add a good value for you.
Next course to complete the topic for network programmability and automation for Huawei Datacom products is Huawei Network Automation, Python 3 and Ansible Labs.
We will start our course by installing Python 3 for Ubuntu Linux. Python 3 basics are important to be able to build automated scripts with Python 3. We have to have good information about if statement, dictionary, for loop, input function, lists, read from a file, write in a file, and while loop. Next is to use Python 3 Telnet library to automate scripts to configure Huawei router. Next module is Python netmiku. We will have an intro about netmiku and know how to install netmiku on Ubuntu Linux. Finally, how to run netmiku script for Huawei router. Next module is Python Napalm. We will get information about what Napalm is and how to install it, and we will get information about the different APIs of Napalm. Get Facts API, Get Interfaces IP API, and Ping API. Next module is Automate Configuration Tasks, OSPF configuration as an example to make it automated for Huawei routers. We will build automated scripts with Napalm and netmiku to configure Huawei routers with OSPF. Next module is to have some use cases to build automated tasks. The first one is to backup configuration files of Huawei routers. The second one is to build automated app to check if the given IP address is live in the network and configured or not. Next module is netconf. We are going to know what netconf is, how to install it, how to test it, and use netconf to get interface info from the router, configure interface on the router, configure VLAN on the router. Final topic is Ansible. What Ansible is, how Ansible works, install Ansible, basic configuration of Ansible, configure Ethernet trunk with Ansible, save configuration file, and make Huawei batch configuration, and also to check if we can run Ansible playbook files for Huawei NE40E router.
Looking forward to see you enrolled in this course. Let's get started. Welcome to Huawei HCIA Datacom Labs. I am Mohammed Hamdi and I will be your instructor in this course. I have CCIE service provider and I have more than 18 years of experience in IP telecom and enterprise networks worldwide. This course presents the skills required from Huawei engineers to run Huawei Datacom products with advanced IGP and BGP features for enterprise networks. The course is presented in 2 advanced hands-on labs to cover the following main objectives: advanced IGP routing features, OSPF and ISIS routing protocols. This topology will be for Lab 1 advanced IGP features. We will have 3 different areas: Area 0 and Area 1 for OSPF and Area 1 for ISIS. Advanced BGP features: how to configure BGP within the backbone network, how to configure BGP between the backbone network and enterprise networks, and how to secure BGP. This topology will be for Lab 2. We will have 3 different branches for one enterprise network: HQ branch, branch 1 and branch 2. And we will have the backbone network, which consists of 3 different routers, and each router will connect a customer branch. This course is designed for Huawei Datacom engineers. Looking forward to see you enrolled in this course. Let's get started. Lab 1 Advanced IGP features. The objectives of this lab is to configure fast reroute FRR and bidirectional forwarding detection BFD to accelerate OSPF conversions time. Adjust the cost of OSPF routes using route policies. This is the topology of Lab 1 Advanced IGP features. We will have 6 routers connected through 3 IGP areas: PE1, PE2, P1, P2 in OSPF Area 0, P1 and PE3 in OSPF Area 1, PE3 and PE4 in ISIS Area 1. The configuration tasks of this lab will be as following: Task 1 Configure OSPF, Task 2 Configure ISIS, Task 3 Adjust the OSPF cost of interfaces between PE2 and P1, Task 4 Enable OSPF IB-FRR on PE2 to generate a backup route to P1. Task 5 Enable BFD in the OSPF Area 0 to speed up OSPF conversions. Task 6 Create same loopback 2 interface on PE1 and P2 and enable OSPF on them. Task 7 Check OSPF equal cost routes on P1 and limit the number of equal cost route to 1. Let's get started with task 1 of the lab, which is to configure OSPF. This is the lab topology implemented on Eve NG. I will configure OSPF Area 0 for PE1, PE2, P1 and P2 interfaces connected between these 4 OSPF routers, and I will configure OSPF area 1 between P1 and PE3 on this interface. This is the configuration script I have prepared for OSPF configuration. I will configure loopback 0 address as the router ID. This is for any OSPF router, and I'll set the OSPF process to be process 1. The process ID is 1, and I'll enable OSPF on the needed interfaces with the proper area ID as shown in the lab topology. For PE1, to configure OSPF process, we will add on the system view mode OSPF and the OSPF process ID 1, so OSPF 1, and the router ID. The router ID is the loopback of the router. So the loopback of PE1 is 10.0.1.1. We can double check this. On PE1, we can issue command display IP interface brief, and we can see that loopback 0 has IP address 10.0.1.1/32. So the IP address 10.0.1.1 will be the OSPF router ID for PE1. So inside OSPF process ID 1, I will add area 0, and I will quit from the area view, and I will quit from the OSPF view. So we have on PE1 just only one area ID 0. As in the topology, we have PE1 is only in OSPF area 0, and I'll enable OSPF on the needed interfaces. On loopback 0, I will enable the OSPF process ID using command OSPF enable and the process ID 1 and the area ID area 0. This is under the loopback interface. And on the interfaces connected to the other OSPF routers, we have 2 interfaces, Ethernet 100 and Ethernet 101. Both interfaces are in OSPF area 0 and the process ID is 1. So I'll add command OSPF enable 1 area 0 under each interface of them. To double check that, in the lab topology, we will have 2 interfaces, 101 from PE1, and this interface is connected to 101 on P1. And we have another interface, which is Ethernet 100, which is connected to PE2 100. And the 2 interfaces are in OSPF area 0. Let's copy the script of the OSPF for PE1 now and paste it into the configuration view or in the system view mode of PE1. Right click to paste the copied script. To double check that the OSPF is already configured, we can issue command display current configuration OSPF, and this is the OSPF process ID 1 that it's just added, and we can issue command display OSPF interface. We have 3 interfaces, Ethernet 100, Ethernet 101 and loopback 0. I'll do almost the same configuration on PE2, but with it changing the router ID, because on PE2 we have different IP address for the loopback interface, which is 10.0.2.2 on PE2. We can double check that on PE2. Display IP interface brief, and we can see that loopback 0 on PE2 has an IP address 10.0.2.2. This is the router ID of the OSPF that will be configured on PE2. And we have area 0, and we have 3 interfaces to be enabled with OSPF, the loopback 0 interface and Ethernet 100, Ethernet 101, all in area 0. Let's back to the topology to check that. We have on PE2 Ethernet 101 and Ethernet 100, which is correct. This is to be enabled for OSPF area 0 plus the loopback interface of PE2, which is loopback 0 interface. So I'll copy now the configuration of the OSPF for PE2 and paste it in the system view mode. Right click to paste the copied configuration. And Let's now switch to another router, which is PE3. It will be configured with OSPF1 router ID and the loopback interface of PE3. And PE3 OSPF process will have just one area, and the area ID is area number 1. Area 1, not area 0, as in PE1 and PE2. In the lab topology, we have here PE3, and PE3 interface 101 is in OSPF area 1, just area 1. So I will have to enable OSPF area 1 for Ethernet interface 101. This is the prepared script for PE3. Interface loopback 0 will be enabled with OSPF enable 1 area 1, and interface Ethernet 101 will be enabled with OSPF 1 area 1. Let's copy this script and paste it into the system view mode of PE3. Before pasting the copied script, I will double check the loopback interface IP address of PE3, loopback 0, and it has IP address 10.0.3.3. And in the system view, I paste the copied script by right click. And next router to enable OSPF for it is P1, and it has two areas, area 0 and area 1, and its loopback IP is 10.0.5.5. This is the OSPF router ID for P1, and it will have two areas, area 0 and area 1. On P1, we have one interface, Ethernet 101, should be configured in OSPF area 0, and Ethernet interface 100 should be configured in OSPF area 0, and Ethernet interface 102 should be configured in OSPF area 1. And the loopback interface will be enabled in OSPF area 0. This is the script: loopback 0 in area 0, Ethernet 100 in area 0, Ethernet 101 in area 0, and finally Ethernet 102 in area 1. I'll copy this script now and paste it into P1 router. Finally, P2 router. P2 router has only one area, which is area 0. P2 resides in area 0 with its interfaces. All of its interfaces in OSPF area 0, Ethernet 100 and Ethernet 101, plus the loopback interface of P2. This is the script. I'll copy it and paste it into system view mode of P2. Last section of this task is to check that OSPF peering is established properly by using command display OSPF peer brief, and the OSPF routes are being received by the OSPF routers using command display OSPF routing. So I'll copy the first command, display OSPF peer brief, on PE1. I can see that on PE1 that there are two peers recognized, and the two peers in area 0, the two peers are 10.0.2.2 and 10.0.5.5. 10.0.2.2 is PE2 and 10.0.5.5 is P1. Let's back to the topology, and P1 should form OSPF peering with two routers as seen in the result of the display command, P1 and PE2. We can use the same command on P1, and we expect to have three peers: peer with PE1 in OSPF area 0, and peer with P2 in OSPF area 0, and peer with PE3 in OSPF area 1. Let's run this command on P1. Display OSPF peer brief, and as expected we have three peers in area 0, P2 and PE1, and in area 1 PE3. In P2 we can use command display OSPF routing to check on the OSPF routes that are received on P2. we have all the routes expected. This is the OSPF routing table on P2 with their types: next hop, advertising router, area ID, and cost. Let's implement task number 2, which is to configure ISIS. This is the lab topology on EVE-NG, and we have ISIS area 1 between PE3 and PE4 on interface Ethernet 100 on each router of them. So we have to configure ISIS on PE3 and PE4 and enable ISIS on the interfaces Ethernet 100 from both sides, from PE3 side and from PE4 side. And we have to enable loopback 0 on PE4 with ISIS, so that loopback 0 of PE4 can be advertised in ISIS and can be received on PE3. Remember that PE3 loopback 0 is already advertised in OSPF area 1, as in the script discussed before. Now it's time to configure ISIS. The ISIS process ID will be ID number 1, and the ISIS router must be configured with network address or network ID. The network ID or network address or network entity should be configured with 49.0001, which is the area ID, and the system ID, and finally 00. The system ID will be in this format, will be 0000.0000.000 and finally X, and X refers to the router number. So if we are on PE3, X will be 3. If we are in PE4, X will be 4. And this is the configuration of the ISIS on PE3. We will configure on the system view mode of the ISIS router, PE3 or PE4, ISIS 1. And under the ISIS view, we will add the ISIS router level. In the lab topology, we should have PE3 as level 1, 2, and we should have PE4 as level 1. So under ISIS 1 on PE3, we will configure ISIS level and level 1, 2, and on PE4, we will configure IS level as level 1. And on PE3, under ISIS 1, we will add the network entity 49.0001.0000.0003.00, and same on PE4, but the difference in the router number, in the last digit of the system ID. And we will enable the interface with ISIS. From PE3 side, Ethernet interface 100, and we will add command ISIS enable 1 under the interface. And on PE4, we will have two interfaces, 100 enabled with ISIS and loopback 0 enabled with ISIS. Finally, we will check that the ISIS peer is properly established between the two routers, and the ISIS routing table is already formed and can receive routes between PE3 and PE4. So let's copy the script now. I'll copy the script one by one. The first section is for PE3. Right click on it, copy, and go to PE3, system view immediately, and paste the copied script. And I'll copy the second section for PE4 ISIS configuration and go to PE4 system view immediately, right click to paste the copied script for PE4. Now on PE3, I'll display ISIS peer to check that the ISIS peering is established, and I can receive the peer. This peer is system ID for PE4 and on interface Ethernet 100. We can use same on PE4, display ISIS peer, and we can receive PE3 on interface Ethernet 100 on PE4, and we can use command display ISIS route, and here we have the routing table of the ISIS on PE4, and it has the direct connected network between PE4 and PE3. We can check on that, display IP interface brief, and this is the IP address 10.0.0.26, and this is the IP address, and the subnet mask is 24, and the loopback interface of PE4 is in the routing table. On PE3, display ISIS route, and I have on PE3 two levels. On PE4 just one level, which is ISIS level 1 forwarding table, and on PE3 I have two levels, level 1 and level 2, and network 10.0.0.24/30, which is the interconnect link between PE3 and PE4, is in two levels, level 1 and level 2. This is because PE3 is configured with ISIS level 1 too, and network 10.0.4.4, which is the loopback IP address of PE4, and it's only existing in the ISIS level 1 routing table. This is because this loopback interface is configured on PE4, and PE4 is only configured as level 1 router.
Task 3. Adjust the OSPF cost of interfaces between PE2 and P1. We have to check on the route to network 10.0.5.5, which is the loopback 0 of P1, and the checking of this route from PE2. So here we will be on PE2, and we will check on the route to the loopback 0 interface of P1. On PE2, display IP routing table 10.0.5.5. We can see the route to the network 10.0.5.5 over two routes. One route through interface Ethernet 101 and another route through interface 100. Both routes on same cost 2. So on PE2 we have one route through interface Ethernet 101 and another route through interface 100, and the total cost of each route, this is the first route, cost 2. Each link has cost 1, OSPF cost 1. This is a link, one link between PE2 and P2, and this is another link between P2 and P1, and each link has OSPF cost 1. The total cost of the route is 2, and same through the second route. We have two links, and each link has OSPF cost 1. This is why we can see that there are two equal cost routes, and there is load balancing over the two routes to get the network 10.0.5.5. We can check display interface Ethernet 101, and this is interface 101, and it's in up state, and the maximum transmit unit is 1500, and it has an IP address 10.0.0.9/30. And we can check display OSPF interface Ethernet 101, and we can see that the interface 101 is in OSPF process 1 and is in area 0, and it has IP address 10.0.0.9, and it has cost 1. Each Ethernet interface has OSPF cost 1. This is why the total cost of the route is 2. We can also check display
OSPF routing, we can see here two routes to the same network, 10.0.5.5, and cost 2 for each route. And we can select only the network 10.0.5.5 and its subnet mask 32 using this command, display OSPF routing 10.0.5.5 space 32, which is the subnet mask. Copy and paste on PE2, and we can see that there are two equal cost routes to the same destination, 10.0.5.5. And also we can use command display IP routing table 10.0.5.5. We can see here that there are two routes in the routing table of PE2. Next step in task 3 is to adjust the OSPF cost of interface from PE2 to P2. We have interface Ethernet 101 from PE2 connected to P2. It will be adjusted with OSPF cost 2. This will make the route through interface 101 with higher OSPF cost. So on PE2 we will configure interface Ethernet 101 with OSPF cost 2. So the link between PE2 and P2 will be OSPF cost 2 plus the link between P2 and P1 with OSPF cost 1. So the total cost of the route from PE2 to P1 through interface 101 will be 3. This will make higher cost, which means the other route through interface 100 will still have the total cost of 2, which is better than 3. So we will have only one route as main from PE2 to loopback 0 interface of P1 through interface 100. And the second route will not be selected as best route. I'll copy the prepared script for PE2, interface Ethernet 101, and inside interface Ethernet 101 we will configure OSPF cost 2. Copy and go to the system view mode of PE2 system view immediately and paste the copied script. And I'll check again, display OSPF routing 10.0.5.5/32, and we can see only one route, which is through Ethernet interface 100 with OSPF cost 2. And we can also use command display IP routing table 10.0.5.5. And I can see only one route with cost 2 through interface Ethernet 100.
Task 4. Enable OSPF IP FRR on PE2 to generate a backup route to P1. The previous task, which was adjust the OSPF cost of interfaces between PE2 and P1. We had two equal cost routes to 10.0.5.5, and these two equal cost routes was from PE2, and we changed the cost of interface from PE2 to P2 to make only one route as best route. So on PE2 currently we have one best route preferred to P1 loopback interface, which is through PE1, and the other route, the second route, which is through P2, is not preferred because of its higher cost. Now I will configure on PE2 IBFRR. IBFRR let the router to have one backup route ready to be used when the main route is not available. On PE2 we will configure OSPF IBFRR using command loop free alternate under FRR under OSPF1. So we will configure OSPF1 on the system view of PE2, and under OSPF view we will add command FRR and we will press enter, and under FRR view we will add command loop free alternate. Then we will quit
from the FRR view, and we will quit from the OSPF view. And we will check the route to network 10.0.5.5 using these two commands: display IP routing table 10.0.5.5 and display OSPF routing 10.0.5.5 and its subnet mask 32. Let's go to the configuration of PE2. We will add command system view immediately, and I'll copy the prepared script for PE2, right click on it, copy, go to the system view of PE2 and paste the copied script. And I'll use command display IP routing table 10.0.5.5. I'll copy it and paste. I still have only one route, which is the main and best route used for 10.0.5.5/32, and it's through Ethernet 100, which is through this interface. PE2 goes to PE1 through interface Ethernet 100 to get the loopback interface of P1. This is as before because it has the best cost and the lower cost 2. Now I'll copy the second command, which is display OSPF routing and 10.0.5.5 and its subnet mask, copy and paste on the system view. Now I can see the destination, which is 10.0.5.5/32, the loopback interface on P1, and it has cost 2, and the next hop is 10.0.0.1 through interface 100. This is the main route, and we have a backup next hop. The new thing here that we configured IPFRR, and we can maintain the backup route to network 10.0.5.5/32 and its backup route through the backup interface Ethernet 101. And we have the backup type LFA link node. Now if the main OSPF route to network 10.0.5.5 went down and is not available, PE2 can switch to the backup next hop 10.0.0.10 in order to get 10.0.5.5/32. Task 5. Enable BFD in the OSPF area 0 to speed up OSPF conversions. In the previous task, we configured IPFRR on PE2, so PE2 can have a main route to destination 10.0.5.5/32 and a backup route to same destination through backup next hop 10.0.0.10 and the backup interface Ethernet 101. So if the main route to network 10.0.5.5 is faulty, PE2 can switch to the backup next hop or the backup route. What time PE2 will wait until it can make sure that the main next hop or the main route is unavailable? If we issue command display OSPF pair, we can see the pair 10.0.0.1, which is the main route or the main next hop to network 10.0.5.5. And we have dead timer. The dead timer is 38 seconds. The total dead timer is 40. But according to issuing this command, it was 38. This dead timer reset to 40 when it receives a hello packet from the peer 10.0.0.1. So if there was no hello messages from the peer due to any failure with the peer, PE2 will have to wait 40 seconds until it can use the second or the backup route. This time could not be accepted. It's long time to switch or to restore. It's long time to switch or to restore the service to the backup route. We can issue this command again, At this time it's 33 seconds. Here it's changing. Here it's 32 and here it's 38 again. So it's changing. In order to make PE2 to detect that there is a failure with a pair quickly, we have to use BFD and we have to configure BFD to inform the OSPF protocol on the router that there is a failure. To do that, we have to enable BFD on the OSPF routers. As in the task, we have to configure BFD for OSPF routers in area 0. So in the topology, we have to configure BFD for PE1, for PE2, for P1, for P2. And we have to configure BFD for OSPF for the 4 routers in area 0. Back to the script, we have to configure BFD on the system view of the router, BFD, and we quit from the BFD view, and we have to go to the OSPF process, OSPF 1. OSPF process 1 is added for all the routers, and we have to configure BFD all interfaces enabled under OSPF. And on each interface enabled with OSPF, and we have to add these 2 comments, OSPF BFD enable, and we have to configure the timers for BFD. In the task, we have to set the minimum interval for BFD packets to be sent and received to be 500 milliseconds, and the local detection multiplier to be 3, which means 500 multiplied by 3, 1500 milliseconds. The router has to wait for 1500 in order to declare that there is a failure, which is quite better than 40 seconds. So to configure the timer under each interface, we add command OSPF BFD and minimum TX interval 500, minimum RX interval 500, and detect multiplier 3. So let's copy the script. I'll copy the BFD section and the OSPF section. I'll copy this prepared script and paste it into all OSPF routers in area 0. In PE1, system view immediately and paste. I'll quit here and do the same on PE2 and on P1, system view immediately, do same, and on P2, system view immediately and do same. Now I have configured PE1, PE2, P1 and P2 with the global configuration for BFD and for the OSPF process. Now I'll go to each interface and enable BFD for OSPF and set the required BFD timers on each OSPF interface. For PE2, I'll configure Ethernet 100 and Ethernet 101, and PE1 same, Ethernet 100 and Ethernet 101, and P1 same and P2 same. I'll configure PE2 on this video, and I'll configure offline the other 3 routers. The other 3 routers have same configuration as PE2. I'll copy the configuration for the interfaces and paste on PE2 system view. I have here error appeared on detect multiplier. I'll double check on this and I'll configure OSPF BFD minimum TX interval 500, minimum RX interval question mark 500 and detect multiplier 3. I forgot to add 500 after minimum RX interval, and I'll do same for Ethernet 100. Don't forget to save your configuration, and I'll do same offline for PE1 P1 and P2. Before doing that, I have to update my script to have 500 after minimum RX interval. This is for PE1 and we have no errors here. Save the configuration and I'll make same script for P1 and P2 offline. We have to verify that the BFD sessions for OSPF is working using command display OSPF BFD session all. I'll copy display OSPF BFD session all command and check on PE2. Now I can see that there are two BFD sessions. The BFD session state is up for the first peer over interface Ethernet 100. The local IP address is 10.0.0.2. The neighbor ID is 10.0.1.1, the loopback address, and the remote IP address of the peer is 10.0.0.1, and we have RX interval 500, TX interval 500, and the local multiplier is 3. And we have another BFD session in the up state with the other peer through interface Ethernet 101, and the local IP address is 10.0.0.9, neighbor ID is 10.0.6.6, remote IP address is 10.0.0.10, and RX interval 500, TX interval 500, and multiplier is 3. Task 6. Create same loopback 2 interface on PE1 and P2 and enable OSPF on them. We have to enable OSPF on the interface loopback 2, and that has to be done on PE1 and P2. Let's go to the lab now to implement this task. This is the script I have prepared for PE1 and P2. We will configure interface loopback 2, and this is the IP address of the interface 10.2.16.16, and subnet mask is 32. And this configuration will be done on two devices, PE1 and P2, and the loopback interface will be enabled with OSPF process number 1 and area 0. Let's go to the network topology of the lab. We will configure the loopback interface on PE1, and we will configure the same loopback interface on P2, and both loopback interfaces with same IP address and will be advertised from both devices, PE1 and P2, using OSPF. Let's copy the prepared script and paste it into PE1 and P2 system view mode. I'll copy interface loopback 2 and the IP address and OSPF enable 1 area 0. Copy and paste into PE1 and P2. This is the system view on PE1. I'll paste the copied script and I'll press enter, and I'll do the same on P2. System view immediately to go to the system view of P2, and I'll paste the copied script. Task 7. Check OSPF equal cost routes on P1 and limit the number of equal cost route to 1. Only one route will be accepted on P1 for any OSPF equal cost routes. If on P1 received 2 or more equal cost routes to same destination, after limitation, P1 will only accept only one route. Let's go to the lab to check the OSPF equal cost routes on P1 and implement the limitation of equal cost routes to 1. I will check the OSPF routing table on P1 using display OSPF routing. I'll copy this display command and go to P1. Paste the copied display command and press enter. I can see that there are two routes to to same destination, which is loopback to interface 10.2.16.16/32, and the first route through next hop 10.0.0.5, and the second route is through 10.0.0.14. If I issued command display IP routing table 10.2.16.16, I can receive same two routes, and the first route through interface 101 and the second route is through interface 100. Let's go to the network topology of the lab. We are on P1 and we can receive the loopback to interface from interface 101 and from interface 100, from PE1 and from P2, because same loopback to interface is configured on PE1 and P2. So we can receive same cost for the two routes, and this will lead to have two equal cost routes to same destination. Now I limit the number of equal cost routes to 1 on P1. On P1 I'll go to the OSPF1 configuration, OSPF process, and press enter, and under OSPF process 1 I will add this command, maximum load balancing 1, to only set the number of equal cost routes to 1. That will make P1 to only accept just one route if it has two equal cost routes to same destination. I'll copy this configuration, OSPF1 and maximum load balancing 1, right click, copy and paste inside P1. I forgot to go to the system view. System view immediately and paste the copied script. Now I have applied the required configuration to only accept just one route to same destination. Let's see how the router will select just one route. On the network topology of the lab, on P1, it will receive the route from PE1 and from P2. Which route will be accepted? There is a process to let P1 to select only one route if it has two equal cost routes or more, or it will select just one route randomly. The answer is that there is a process on the router to only select just one route if it has two equal cost routes or more. Valid routes are selected for load balancing if routes exceeded maximum number allowed for load balancing routes, which is our case. We have two routes and we selected only one to be accepted for load balancing. So the OSPF router will select based on the following. Policy number 1, routes with highest priority, which is lowest weight. We have two equal cost routes through OSPF, so we will have two equal cost OSPF routes. So we expect to have same weight or same priority. Policy number 2, if routes with same priority, routes from largest interface index. The routes are received on different interfaces and each interface has an index. The interface with the largest interface index is preferred and it will be selected. Number 3, if routes with same priority and same interface index, the routes with the largest next hop IP address will only be selected. So now I'll check on each interface on P1 that will receive the equal cost route, and I'll check its interface index. On P1 we have interface Ethernet 101 and we have interface Ethernet 100. Display on P1 interface Ethernet 100. We can see that on the first statement there is IF index 6, which is the interface index is 6 here. This is for Ethernet interface 100. And display interface Ethernet 101. This is the second interface that it's receiving the second route, and interface 101 has interface index 8, which means interface index 8 for 101 is larger than interface index for 100. So we expect, based on policy 2, that Ethernet interface 101 will be selected. Back to the topology, P1 should prefer the route from interface Ethernet 101, which is from PE1. Let's double check that using command display OSPF routing I'll copy this command again. On P1, paste display OSPF routing, and we can see that only one route is accepted for 10.2.16.16/32, and the next hop is 10.0.0.5. The advertising router is 10.0.1.1, which is PE1, and this is correct as expected because PE1 is connected to interface 101 on P1, which has the largest index. And we can double check that on PE1, it should have its interface 10.0.0.5 connected to P1. Let's check that. On PE1, display IP interface brief, include the copied IP address, and it's configured on Ethernet interface 101 on PE1. Let's go to the network topology of the lab, and on PE1 we have Ethernet 101 configured with this IP address, and it's connected to P1. So this is the correct next hop preferred to be selected as the route for the loopback 2 interface. This is the topology of Lab 2 Advanced BGP features. We will have 4 different autonomous systems. The backbone autonomous system 65100, and it will have 3 routers, P2, PE2 and PE4, and we will configure OSPF area 0 in the backbone autonomous system, and we will have 3 different branches as enterprise networks. The first branch HQ AS 65103, and it will have just one router, P1, and P1 will be connected to P2. And the second branch, branch 1, AS number 65001, and it will have PE1 router connected to PE2, and branch number 2 in AS number 65002, and it will have PE3 connected to PE4. The configuration tasks of Lab 2 will be as following. Task 1, configure BGP between the backbone and enterprise networks. Task 2, configure BGP GTSM, generalized TTL, security mechanism and authentication to ensure securing BGP. Task 3, configure iBGP on the backbone network, P2 as root reflector, PE2 and PE4 as clients. Task 1, configure BGP between the backbone and enterprise networks. This is Lab 2. We have HQ, branch 1 and branch 2. These are the enterprise networks, and these enterprise networks are going to connect to the backbone network through BGP. So each enterprise network has its own autonomous system. HQ has autonomous system 65103, branch 1 has AS number 65001, branch 2 has AS number 65002, and they are going to connect to the backbone routers through BGP, and the backbone has autonomous system 65100. So different autonomous systems connect through eBGP or external BGP. This is task number 1, is to configure eBGP between each enterprise branch and the backbone router. So HQ P1 is going to connect through eBGP with P2, PE1 is going to connect through eBGP with PE2, and PE3 is going to connect to PE4 through eBGP. I have prepared the script for this task to establish eBGP peering through loopback 0 address. So each router is going to connect through loopback 0, and we will use loopback 0 on each router as the BGP router ID. So P1 loopback 0 is going to connect with eBGP to loopback 0 on P2, and same for the other two eBGP peering. There is no routing for the loopback, so we will configure static routing. On P1, we need to get the loopback address of P2. The loopback address of P2 is 10.0.6.6. This is why I have to configure IP route static route on P1 for the destination network, which is the loopback address of P2, 10.0.6.6, and its submask /32, and the next hop address. The next hop address is 10.0.0.14. On P1, the next hop address is the IP address on interface Ethernet 100 on P2. Let's check that. On P2, display IP interface brief, and we can see that Ethernet 100 on P2 has IP address 10.0.0.14. This is the next hop address for P1 to get the loopback address of P2, which is 10.0.6.6. And on P2, we have to configure a static route to the loopback address of P1. On P1, display IP interface brief, and the loopback address of P1 is 10.0.5.5. And the next hop address for P2 to get the loopback address of P1 is the interface Ethernet 100, which is 10.0.0.13. Back to the topology, and this is the interface that we stated. It's Ethernet 100, and this is the static route that will be configured on P2. So let's copy the first static route on P1 and paste it into the system view of P1. And I'll copy the static route that should be configured on P2. This is the loopback address of P1, 10.0.5.5. So on P2, we will go to the system view using system view immediately, and I'll paste the static route. Now P2 can get the loopback address of P1, and same for P1 can get the loopback address of P2. We can test that using ping and -a and the source IP address. I will initiate a ping request on P2 with a source address of loopback 0, which is 10.0.6.6. And the target IP address or the destination IP address will be the loopback address on P1, which is 10.0.5.5. And now I can get reply, so it means that the routing over the loopback addresses between P1 and P2 are working properly. I will do the same for the other routers. On PE1, I'll configure a static route to point to PE2 loopback address. Right click on it, copy and paste into PE1. We have to go to the system view, and I'll paste the static route. This is the static route for loopback 0 on PE2. And on PE2, I'll copy this static route for the loopback address of PE1. System view immediately, and I'll paste the static route. And now I can ping -a 10.0.2.2, and the target IP address is 10.0.1.1. And I can ping last two routers, PE3 and PE4. I'll copy the static route for PE3, system view immediately, and I'll paste the static route for the loopback 0 interface of PE4. And I'll do the same for PE4, copy and paste inside system view of PE4. Paste, and we can test the connectivity using ping -a 10.0.4.4. This is the loopback 0 interface of PE4, and the target is the loopback 0 of PE3, 10.0.3.3. And now I can ping. Next is to configure the eBGP peering between each two routers, P1 and P2, PE1 and PE2, PE3 and PE4. On P1, I will configure the BGP with its autonomous system number, or the AS number is 65103. This is for P1. And the router ID is the loopback 0 address of P1, which is 10.0.5.5. I'll configure the BGP router ID using command router ID under the BGP view. Router ID and the IP address is 10.0.5.5. After that, I'll configure the peer. Here, the peer will be the loopback address of P2, which is 10.0.6.6, and its AS number is 65100. After that, I'll press enter and I will configure the peer with command connect interface loopback 0. Peer and the peer address and connect interface loopback 0. This is to guarantee that the source of the BGP packets that will be sent from P1 will be with the IP address of loopback 0 of P1, because the loopback 0 of P1 will be configured on P2 as the target IP address for the eBGP peering. So I must guarantee that the source is loopback 0 on P1 and same on P2. Here I must guarantee that the source of the BGP packets is loopback 0 of P2. Otherwise, the eBGP peering will not be established. On P2, we will configure the BGP peering, the BGP AS number 65100, the router ID is loopback 0 of P2, and here the peer 10.0.5.5 with its AS number, and the peer with connect interface loopback. I'll copy the prepared script for P1, right click on it, copy and paste inside the system view of P1. Here I have got an error that BGP is already running and its AS number is 65001. AS number must be 65103. I'll double check the configured BGP, display current configuration, configuration BGP, and here I can see just BGP 65001. I cannot configure two different AS number on the same router. So I will remove this AS number, undo BGP and the AS number 65001. It's warning me that BGP process will be deleted and it asks me to continue. I will press yes. I'll copy again the configured BGP script for P1 and paste. Now I have configured the prepared script for BGP on P1. I'll do the same for P2. I'll copy this configuration script for BGP to be configured on P2. I'll copy and go to P2 and paste here. And I will do the same on PE1 and PE2. BGP 65001, this is for PE1, and the router ID 10.0.1.1, and the peer address is 10.0.2.2, which is the loopback 0 interface of PE2, and its AS number 65100, and last comment is peer, the peer address, and connect interface loopback 0. I'll copy this prepared script, go to PE1 and paste. And I will do the same on PE2. Router ID is loopback 0 of PE2 and the peer address is PE1. And I will do the same on PE3. I'll copy the configuration for PE3 to pair with PE4. And last router is PE4. I'll copy the prepared script for PE4 and paste it into PE4. Now I have finished adding the required eBGP configuration to establish eBGP peering between the enterprise networks and the backbone network. Back to the topology. On PE2, I will check that BGP peering is established with PE1, and I will do the same on P2 to check that the eBGP peering with PE1 is established, and I will do the same on PE4 to check that eBGP peering is established with PE4. The command that is used to check eBGP peer relationship is display BGP peer. I'll copy this command and paste it into the three routers of the backbone network: PE2, P2, and PE4. Here I can see that the peer is added, but with state idle. On P2, display BGP peer, and I can see that the peer is still idle as well with P1. And same for PE4, display BGP peer, and I can see the peer but with idle state, not established. The eBGP peering between the routers didn't come up. We have to troubleshoot and check the configuration. We have to make sure that on P1 we configured the loopback address of the target router P2 correctly with its correct AS number 65100. Let's check that on P1. I can see that the BGP AS number is 65103 on P1, and the local loopback address of P1 is configured correctly, and we configured the target loopback address of P2 correctly, 10.0.6.6, and its AS number is 65100. But display BGP peer, I cannot see the BGP peering in established state. I can see it's in idle, which means that it's not working. We have to know that eBGP peering working only on the direct physical interfaces. This is by default. eBGP peering can be established just on the physical direct interfaces. But in our example, we configured the loopback address of P1 as the source from P1, and the destination is the loopback address of P2. And we did same on P2. We configured the local loopback address of P2 as the source of the BGP, and the target or the destination of the BGP is the loopback address of P1, which makes that P1 and P2 trying to establish eBGP peering on non-direct interfaces. In this case, eBGP peering will not be established by default, and we will face the same issue between PE2 and PE1, and between PE4 and PE3. To recover this issue, we have to configure eBGP maximum hops to configure the hops allowed for the eBGP to establish between non-direct interfaces. So if we configured the maximum hops as 2, the eBGP peering should be working. Because for loopback interfaces, if loopback interfaces are used to establish eBGP peer relationship, the peer eBGP maximum hop command must be configured with more or equal to hops so that the peer relationship can be established. Because if one hop, it means that it's a direct connected interface. So we will configure the maximum hops as 2 hops. Let's try that on P1 and P2. On P1, display current configuration BGP. I will add here another command, the peer and the peer address and maximum hops as 2. But before I add this, I will check the BGP peer relationship status. The peer 10.0.6.6 is in idle state. System view immediately on P1 and right click the BGP AS number and copy the peer and the peer address and add the keyword eBGP maximum hop and 2 2 or more is accepted for the eBGP peering that is based on the loopback address. Enter to apply this command, and I will do the same on P2. System view immediately, display current configuration BGP, and BGP 65,100, and I'll copy the peer and paste it here and add eBGP maximum hop 2. Display BGP peer again, on P1 I'll exit and display BGP peer again, and I can see that the BGP peer status is in the established state. Before applying the command eBGP maximum hop 2, it was in idle state. So it must be configured with hops more than or equal to. If is not configured, the eBGP peering must be established on the physical interface. Task 2. Configure BGP GTSM generalized TTL security mechanism and BGP authentication to ensure securing BGP. If we have an attacker set here, this attacker can send BGP messages to the backbone network PE2, P2, PE4, even the enterprise routers that run BGP. BGP attacks can make the BGP router overloaded with many BGP messages. Many BGP messages can cause high CPU utilization. The attacker can pretend to be a BGP speaker by sending many BGP packets to the target BGP speaker. The BGP target router, like P1 or any real BGP speaker, finds that its destination in the BGP packets sent by the attacker, and the forwarding plane of the target BGP router directly send the BGP packets to the control plane without checking the validity of the BGP packets sent by the attacker, and that can cause its CPU to be highly utilized because there are many BGP messages sent from the forwarding plane to the control plane, and these BGP packets are fake BGP messages sent by the attacker. GTSM, generalized TTL security mechanism, protects the router against BGP attacks by checking the TTL value in the received IP header. The BGP messages sent by the attacker has IP header, and this is the BGP message. In the IP header there is TTL, or time to live. So GTSM checks the TTL value in the received IP header. If this value doesn't match with a predefined range of the TTL of the receiving router, BGP packets are dropped. In the router, we will configure a TTL range, and if the TTL, which is usually a small value sent by the attacker, the BGP attackers usually send BGP messages from the internet, and because the BGP messages travels all over the path from the attacker side until the target side, the TTL value of the IP packet usually is small value. If we configured a predefined TTL range on the router with a high range, it will be higher than the small value sent by the IP packet of the attacker, and that will cause the router to drop the BGP packet sent by the attacker. Thus, it will protect its control and forwarding plane from receiving many fake BGP messages. To configure GTSM, generalized TTL security mechanism, under the BGP view and the AS, and we press enter, then we add the peer and the peer address, and after that we add keyword valid TTL hops, and we add the configured number of hops. We will configure and set the valid TTL hops to be 1, so we will add value 1 after valid TTL hops. This is the command that will enable GTSM feature, and it configures and set number of hops, which is 1. If we didn't add any value, the default value will be 255. The TTL range will be calculated as following: 255 minus the hops configured plus 1. This is the first number in the range, and the last number in the range is 255. So if we added the configured hops as 1, so 255 minus 1 is 254 plus 1, 255. So the range is 255 and 255. So the TTL in the IP packet of the received BGP message must be in this range between 255 and 255, which means the TTL must be 255. So if we configured the valid TTL hops to be 1 on both BGP routers in the network, between HQ router for example and between P2 router, we have to add the configured hop as 1 to be same range, 255 and 255. That will make the two routers to accept BGP messages from each other, and the attacker BGP messages will be dropped. If we added configured number of hops to be 2, that means the valid numbers of hops will be 254 and 255. Any other TTL numbers smaller than this range will be dropped. Another level of security can be added to the BGP, which is BGP authentication. We will add BGP authentication between BGP speakers. That will authenticate only authorized BGP speakers to communicate to each other using command peer address and keyword password and keyword cipher and the password. Keyword cipher is to encrypt the password of the BGP and to not appear as clear text in the configuration file. The BGP authentication password will be Huawei @123. The first letter is uppercase. So in this task, we have added two levels of security: to configure GTSM with valid number of hops as 1 that is needed to each peer, and to configure BGP authentication. Even if the attacker can send an authorized TTL, it will be hard for the attacker to know the configured BGP password. Before I copy this script, I will review the BGP configuration on P1, display, current configuration, BGP, and here we had eBGP maximum hop as 2. This is because the BGP peering between P1 and P2 is established over loopback address, which is not directly connected interfaces between P1 and P2. This is why we had to add eBGP maximum hops as 2. I will remove this command and I will add GTSM feature and BGP authentication password. GTSM feature can be enabled and can replace the function of the eBGP maximum hop. Let's remove now eBGP maximum hop 2. System view or system view immediately, and I'll copy BGP and the AS number, and I will undo peer and peer address and eBGP maximum hop, and I will do the same on P2. Display, current configuration, BGP, system view immediately, and I'll copy the BGP and its AS number, and I will undo the peer and the peer address and the eBGP maximum hop. Now I will reset the BGP peering, and I will do the same on P1. After that, I will issue command display BGP peer to check the BGP peer status, and we can find that it's back again to the idle from the established state. It was in the established state because of adding command eBGP maximum hop 2. But I have removed this command, and now the BGP state back to idle, and same on P2. Now I'll copy the prepared script for the BGP security for P1 and for P2. right click the configuration script for P1, copy, go to P1 and system view immediately and paste here, and back to the script again, copy the prepared script for P2 and paste in P2, system view immediately and paste here, and display BGP peer again, and we can see that the peer now is back to the established state. It was idle before applying the GTSM feature with valid number of hops as 1 and the BGP authentication cipher Huawei at 123. We can issue command display current configuration BGP, and here we can see that we have added successfully to the configuration of the BGP GTSM feature with valid TTL hops as 1, and the BGP password doesn't appear as clear text, it appears as cipher. And I will do same on P1, display BGP peer, and I can see that the peering with P2 is in the established state, and display current configuration BGP, and I can see here same configuration, and we don't have eBGP maximum hop as 2. GTSM is enough for the BGP speaker to establish peering with another eBGP peer over non-direct connected IPs. This is the script for PE1 and for PE2, for PE3 and for PE4. All routers in this task will be configured with valid TTL hops and with same cipher password. I'll copy these configuration scripts and apply them offline. They are same as we did for P1 and for P2. Task 3. Configure iBGP on the backbone network, P2 router as root reflector, PE2 and PE4 as clients. Here in the backbone network we have P2, PE2 and PE4, and they are all in the same AS number 65100. We will enable iBGP peering because they are all reside in the same AS number, and we need to enable BGP peering between them. So P2 will pair with PE2 and P2 will pair with PE4. We will configure P2 as root reflector and PE2, PE4 as BGP clients to the root reflector. This is the task. We will establish BGP peering using loopback address as the source IP address, and we will use BGP peer group on P2. This is for simplification. On P2, this is the prepared script, BGP AS number 65100, and we will add peer group using command group, and the group name is PB. This abbreviation is for backbone and internal because we are enabling iBGP between the routers, and the routers will be added to this peer group as internal peers, and we will configure the peer group to connect with interface loopback 0 using peer and the peer group name and connect the interface loopback 0, and we will add next hop local for each peer that will join this peer group. This is to announce the routes to the peers that will join this peer group with the local next hop from this router P2. And next two commands is to add the peer addresses to the peer group BB or backbone using command peer, and the peer address is 10.0.2.2, which is the loopback address of PE2, and we will add the loopback address of PE4 to peer group backbone on P2 using command peer and the peer address, the loopback address of PE4 and the group and the group name. After that, we will add command IPv4 family unicast, and under IPv4 family unicast we will add the peer and the peer group and reflect client. This is to define each peer that will join the peer group BB as client to P2, which is the root reflector. On PE2 we will add the IBGP peering to P2 normally, just like adding a new peer. So under BGP and the AS number of PE2 65100, which is same as the AS number of P2, we will add the peer and the peer address of P2, which is 10.0.6.6, and the AS number 65100. And then we will add connect interface loopback 0 to the peer address of P2, and we will add next hop local. This is to announce any routes to P2 with the local next hop address of PE2. And we will do the same for PE4 to establish IBGP peering with P2. I'll copy this script now for P2. Right click on it, copy and paste inside the system view of P2. System view immediately and paste here. And don't forget to save the configuration. And now I'll copy the script for PE2 and paste it into the system view of PE2. System view immediately, paste and exit and save here. Don't forget to save your configuration whenever you add new configuration. And same configuration for PE4, system view immediately and paste here. And don't forget to save the configuration. And we will use command display BGP peer to check the IBGP peer relationship. Copy and paste in P2, and we can see now that there are two new peers in the established state, and these two peers are IBGP peers, and the first peer was P1. It was established earlier, and we can do the same check on PE2 and PE4. Here we have two peers. The first peer is PE1, which is established earlier, and the second peer is P2, which is just established using IBGP peer. And we can do the same check on PE4, and we have two pairs.
Welcome to Huawei HCIA Datacom Labs. I am Mohammed Hamdi and I will be your instructor in this course. I have CCIE service provider and I have more than 18 years of experience in IP telecom and enterprise networks worldwide. This course presents the skills required from Huawei engineers to run Huawei Datacom products with advanced IGP, BGP, MPLS VPN and EVPN features for enterprise networks. The course is presented in 4 advanced hands-on labs to cover the following main objectives. 1. Advanced IGP routing features, OSPF and ISIS routing protocols. This will be the topology of Lab 1, advanced IGP features. We will have 3 different areas, Area 0 and Area 1 for OSPF and Area 1 for ISIS. 2. Advanced BGP features, how to configure BGP within the backbone network, how to configure BGP between the backbone network and enterprise networks, how to secure BGP, how to configure BGP policies to control routing between branches, and how to limit BGP received routes. This will be the topology of Lab 2 advanced BGP features. We will have 3 different branches for one customer, HQ branch, branch 1 and branch 2. And we will have the backbone network. In the backbone network, we will have 3 routers, each router in the backbone network to connect one customer branch. 3. MPLS VPN, how to configure MPLS in the backbone network, how to provide layer 3 VPN service for enterprise customers. 4. Ethernet VPN, EVPN, how to provide EVPN, layer 2 and layer 3 services to enterprise customers based on MPLS. This will be the
topology for Lab 3 and Lab 4, MPLS VPN and AVPN. We will have 3 different branches for one customer, HQ branch, branch 1 and branch 2, and we will have the backbone network. In the backbone network, we will have 3 different routers, each router to connect one customer branch, and we will provide the required MPLS L3 VPN service provided from the backbone network. And for the EVPN, we will provide layer 2 and layer 3 service for the EVPN to connect the customers in 2 different scenarios, layer 2 and layer 3. This course is designed for Huawei Datacom pre-sales, post-sales and network architects who want to be competent with the expert positions of full scenario enterprise networks. Looking forward to see you enrolled in this course. Let's get started.